idea here from last week is we want to get this to be something like a over 1 minus r. So, I mean, I would just say 1 over 1 minus x to the third, right? So then that tells us that, you know, a is 1 and r is negative x to the third. So now we can throw all of that stuff together and we can say that that's going to be the sum as n goes to 0 to infinity of a, which is 1, so that doesn't really do anything. And then we're going to do negative x to the third to the n. And we can clean that up a little bit if we wanted to, right? Because of that negative thing there. So we'll say that's 0 to infinity of, and then that would be negative 1 to the n, and then x to the 3n. There's your power series, and the interval of convergence is negative 1 to 1. That's all there is to know. So even though that looks maybe like a challenging one, it's actually not too bad. It's pretty easy. Just make sure you pull that alternator piece out if you could. Number 2, so here's what I would do, is I would go ahead and think of this as x times 1 over 5 minus x. Furthermore, you could then think of that as x times 1/5 over 1 minus x to the 5. So now what we can do with this blue stuff is say that a is 1/5 and r would be x over 5. So the blue thing is going to be 1/5. We're going from 0 to infinity of x over 5 to the n. We can clean that up a little bit here. And so that's going to move this guy out of the way. So that's going to give us, let's see here, that denominator, instead of being 5 to the n, I can say it's 5 to the n plus 1. So I can say that this is the summation of n equals 0 to infinity of x to the n over 5n plus 1 exponent. Oh, but don't forget that there's an x there. So now I can just add an additional factor, if you will, to the exponent there. So instead of x to the n, it's just going to be x to the n plus 1. And I guess if you wanted to, you could just say it's x over 5 to the n plus 1. It's one way to write it. Okay. Interval of convergence there is negative 5 to 5. Okay. Questions on the warm-up? This is just kind of review stuff from last week. Again, these are just slightly different than maybe some of the stuff we did on the homework, just to make sure that we're going in the right direction. And again, I think when I wrote my final answer, and you don't have to write this down, I think when I wrote my final answer, I wrote it as, 1/5 to the n plus 1, and then I did x to the n plus 1. That's how, I think, kind of how I wrote mine, but it doesn't matter. I usually kind of separate the x from the other stuff. Okay. Now, guys, you're going to see me kind of referring a little bit back and forth to my notes here because I don't want to make any careless mistakes because we're going to cover a lot. Some of this stuff should be very deja vu-ish because we are going to hit things that we've already kind of hit conceptually when we did section 8.7, which was on Taylor polynomials. So remember, a Taylor polynomial has how many terms? A finite number, right? We are talking about Taylor series here. So now we're going to talk about, if you want to think about this way, like a polynomial of infinitely many terms, if you will. So we want to find a Taylor or a Maclaurin series for a function. That's one of our objectives. This is going to be the one that I'm going to be checking my notes probably the most, and that is I'm going to try to explain to you the general formula for a binomial series. And then we'll go over some of the basic Taylor series, Maclaurin series, that if you have these memorized, which I would recommend that you do, particularly if you're shooting for a 4 or 5 on the AP exam. Oh, I guess I should mention that again. When is the AP exam? May 4th. That is official. It will be in person. It will be paper, pencil, calculator. I just want to make sure everyone's clear on that. Everyone will be taking that exam here at Perry Marion High School on May 4th. There is not a virtual option. Okay, so we're going to kind of review some of this stuff that we did in the past. Let's say that we've got some function f of x that can be represented here by some power series. We've been talking about power series. This should seem kind of familiar. And by the way, this guy right here, this last piece here we're talking about, there's going to be some remainder there at the end, right? That's what that r is. So let's try to determine the coefficients of c sub n that we must use in terms of our function f. So the first thing we've got to do is we've got to say, what's the function evaluated by a? By the way, a is going to be our center, if you will. Well, it's simply going to be c naught. Now, if we differentiate our series, and by the way, we're talking about this equation here. If we differentiate that, what happens to this term? Bye-bye, gone, right? It's constant. By the power rule, what happens to that term? Well, it's going to fall away and you'll be left with just what? C1 times 1 is just C1. What about this term here? Well, it's going to be 2 times C2, and then this would be x minus 1, or x minus a, whatever it is, to the first anyways. So you're going to get something like this. Now notice the C naught part disappeared because it was just a constant term. Now the linear term has become the constant term. Now here's the key, and again, you guys already know this. What if I did the derivative again? What if I went from the first derivative to the second derivative of the function? Now what happens to C1? Well, it's gone. What happens to, let's kind of skip that second. Look at this term. What's going to happen to that term? Well, now we're going to take that 3 times 2. Times 2. And on down the line. And then here you'll notice this one became 3 times 4. And now, guess what we're getting here? What are we going to get here in front of these constants? Factorials. This is that whole idea of factorial. That's why we started, if you think about it, I even introduced factorials before we started actually talking about these Taylor polynomials, back when we were just doing the ratio tests and all those kinds of things, because that is a natural consequence of that. We did the third derivative. Okay, now the C naught is gone, the C1 is gone, the C2 is gone. Now we've got C3, which is 2 times 3. Now look at C4. By the way, sorry, that was kind of an explosive comment. Anyways, 2 times 3 times, that's that factorial piece. As we keep going, in fact, let's just kind of jump to the chase. This here represents the nth coefficient. The nth coefficient is the nth derivative of our function at the point A divided by n factorial. Now, why is it divided by n factorial? Well, because we have to compensate for that. We have to undo all those derivatives, which means we have to undo all those factors that are popping out, like here. How are we going to undo how do we undo 2 times 3 times 4? Well, we divide it by 2 times 3 times 4. And so that's why we're dividing by the n factorial. So, important theorem right here. Theorem 5. If f has a power series representation expanded at A, then f equals, here's the power series representation, its coefficients are represented here. The nth coefficient will be the nth derivative of the function at A divided by n factorial.
When it says at A, is that at any given number?
Well, it depends on what the center is. So remember, when we're building these, we have to determine what the center is. But yes, it could be any. Well, in our first example, yes, it could be anything. Okay. This is probably the more important formula for you to know. Substituting this formula for the C sub n, the coefficient of the nth term, for the power series. So again, if we came back here to this power series here, there's C sub n. It's the same formula, but this is what you want. This is the general term. Okay? If you think about here, here's where we're getting our coefficients. Here is our x minus the center A to the nth power. This guy gives us what we want. And I'm telling you right now, I can almost guarantee it, absolutely positively, that you will see this on the exam, probably on a multiple choice question. You actually might even see it then. In general, for a function x, f of x, sorry, the first term is just going to be f of a, plus, then you're going to have the first derivative at a divided by 1 factorial times the quantity x minus 1, plus the second derivative at a divided by 2 factorial times the quantity x minus a squared. So guys, what we're doing today is I'm going to try to help you get a more sophisticated understanding of what we did last week. Last week we did power series. In order to do a power series, what do we have to do? We had to have some function that could be written as a fraction that kind of looked like a over 1 minus r. We're going to deal with functions today where you can't do that. So can we make a power series out of that? The answer is yes, kind of. It's called a Taylor series. Special case when a is equal to 0. By the way, when it's a 0, guess what we call it? Maclaurin. Guys, in fact, this should feel very much like deja vu. This should feel very much like section 8.7, except back then we were calling it a Maclaurin polynomial, a Taylor polynomial. So we're just saying now, instead of it just having a finite number of terms, it's going to have infinitely many terms. So let's look at it again. Now, if this had been last week's homework, I would have said, hey, how could we get this to look like a over 1 minus r? And the answer is, you can't. The good news is we're not doomed. So, by the way, it actually doesn't matter. We're just going to, can we just let the center be 0 in this example? So what is f of 0? Okay, great. What is f prime of 0? Now, by the way, what is the derivative of e to the x always? That's why I'm taking this from my first example. So this is a super easy one. So what's f prime of 0 going to be? It's 1. What's f double prime of 0? Anyways, you get the idea, right? In general, f to the nth derivative of 0 is 1. That makes my coefficients very easy, right? Now, I've got to be careful, though. Let's come back to this. This is a very, yeah, actually, this is perfect. I was getting ready to say I almost screwed this up, but I am doing a Maclaurin series here because this is the center of 0. So the formula is, and of course, I could write it like this. I'm going to write it like this, though, here now. So what are we going to have? We're going to have 1 plus, then what's it going to be? 1 over 1 factorial times x plus, what's the next one going to be? 1 over 2 factorial times x squared. Da, 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 da. Does that make sense? I'm using the derivative at 0, the derivative, the second derivative at 0. Anyways, I'm getting all of this here. So now I can go ahead and say that f of x equals e to the x is equal to, and it's going to be 1 plus, what was the next one? Well, 1 over 1 factorial x. The next one, 1 over 2 factorial x squared plus 1 over 3 factorial x cubed. And then what do I need to put at the end? Dot, dot, dot. This is the easiest one I can do, so it's a good place to start. Okay, let me write it a little bit more compactly then. And again, if we wanted to, we could come back here and look at this. So this is going to be the sum, in starting from 0 to infinity. So what would the nth term be? Well, it's just going to be x to the n over n factorial. We can check that. Let's start with 0. If I put 0 in there for n, first of all, what's 0 factorial by definition? What is x to the 0? So there's 1. Now let's put in 1. If n is 1, what's 1 factorial? Well, 1 factorial. What's x to the n? It's just x to the 1, so it's x. And you can check this, and this is it. This is the answer. This is written in a more, the compact way. And up here we have the expanded form, if you will, right? Sometimes it's easier to start with the expanded form. This one's nice because this one, this right here in general for all of them is 1 in this particular case. So that's why I started with that. All right, so the next thing I want to do with this is let's talk about its radius of convergence. By the way, this, look carefully, is just this, isn't it? Let me do it in a different color here. This right here, that's back when we were doing radius of convergence on that's the asymmetries, right? So let's go ahead and figure out what is the radius of convergence for this guy. How do we do that? Well, we do the ratio test, right? So we do the limit as n goes to infinity of the absolute value of a sub n plus 1 divided by a sub n. Again, it should feel very comfortable now. It's like, okay, we've been there, we've done that a bunch, Mr. Allen, we can do this. Okay, so that's going to be the limit. N goes to infinity. Absolute value, which isn't really necessary here, but let's go ahead and put it on there just to be correct. Times, oops, forgot the n plus 1 on the bottom, sorry. Times n, this is factorial. All I've done now, and I've kind of skipped one step, right? I kind of did the division already, multiplied by the reciprocal. So this is the a sub n right here, multiplied by its reciprocal, so that's that. And again, we've played this game so many times, I know it's kind of like, okay, we've been there, Mr. Allen, but just to make sure everyone's clear, that's equivalent to n plus 1 times n factorial. This guy up here is the same thing as x to the n times x, right? Okay, cool. So then that tells us we get the following. We get the limit as n goes to infinity. Well, the x to the n's are going to cancel, so that'll leave you with just an x up there. The n factorial and the n factorial are going to cancel, so you're left with n plus 1. N plus 1 on the bottom. Well, n plus 1, it has, x has nothing to do with that n part, right? So I could basically say it's the absolute value of x times the limit as n goes to infinity of 1 over n plus 1, correct? Now, x could be positive or negative, and that's why I left that absolute value. It doesn't affect the n's. And we, of course, know that this limit is 0, right? It's 0. For which real numbers? All of them. And by the way, 0 is what with regard to 1? Less than 1, right? 0 is less than 1. This is less than 1. But what I'm telling you is that the radius of convergence is infinity. In other words, any real number works for the center. Actually, any real numbers at all. And I just think that's amazing. The radius of convergence is everything. It doesn't matter, which is so nice. I mean, when we looked at the warm-up, we had like that first one, we had a very narrow radius of convergence. I think it was -1 to 1. So that means if I'm trying to use that power series to approximate some decimals, I have to be in that range. Here, I'm telling you that this power series right here converges everywhere. Doesn't matter. You pick the center, it doesn't matter. It works. Very powerful. Anyway, so I tried to review that. Comments or questions on that first? I know that was a pretty easy one. My hope is, though, is you get a general feel for it, and the general feel is this. How do you build a Taylor polynomial or a Taylor series? Just like you built a Taylor polynomial. You do the derivatives, you plug in the value of A, whatever the center is, figure out what those slopes are. You got to put them in, and then you got to remember to divide by these. So I guess kind of, it's not really new stuff. The thing I'm trying to emphasize today are these factorials. Don't forget about those factorials. Those are there. They have to be there. Okay. I'll let that simmer for just a second. The next slide, you see the pink curve? The pink curve, I'll write, actually, I don't know if I've got pink. I guess I'll use red. I'm going to write pink though, even though it's red. The pink curve, that's, f of x equals e to the x. So now if we went back to section 8.7 and we looked at the Taylor polynomials, so here would be the first Taylor polynomial. It's just a line, it's linear. But close to zero, does it give a good approximation for that pink curve? The answer is yes. It actually does a pretty good job. What if I wanted it to be better? Well, I add another term to that Taylor polynomial. And then that, what color is that one? That one looks like it's green. Yeah, it's parabola, right? So it's the green one, the parabola. That's even better. What if I want it better? Well, then you do another term. Now we've got a cubic. That's even better. Those are Taylor polynomials, which are finite. Remember, polynomials, Taylor polynomials, there's a finite number of terms. Now we're going to just say, you know what, let's just pretend we can go forever and make it a series. And that's, guess what that series will do? It will match the curve perfectly. And the beautiful thing is not only will it match it perfectly at zero, it will match it perfectly anywhere you need it to match it. Even out at Graham's number, which I don't even want to guess how many terms that would be, but theoretically you could do that. Okay? All right. If you go ahead and try a little bit with example 2 here. I did example 1. Notice I've got the exact same function. The only difference here is I've changed the center from 0 to 2. Would you go ahead and just take a minute and see if you could hammer that one on and find the greatest of convergence if possible? Okay, if you're still working, I want to kind of take over here because you shouldn't be working too much right at this point. What are you noticing every time you do the derivative of e to the x? What's its derivative? It's always e to the x. So this is the formula, right? This is the formula I gave you a couple of slides ago. So here's my question. What is the nth derivative of this function at 2? It's e to the second, e squared. Everywhere, the constant is e squared. Does that make sense? So that's beautiful. So the only other thing you're going to worry about is putting a 2 in there for this. So what I'm telling you is that f of x equals e to the x when the center is at 2. In fact, let me call it a. When a is 2, is simply going to be the sum, n goes from 0 to infinity, of e to the 2 over n factorial times x minus 2 to the n. That's the answer. Guess what the radius of convergence is? Again, it's still infinity. It's everything. It's negative infinity to infinity. That's the answer. Comments or questions on that? Okay. So, I don't know if you guys can appreciate, before you got to like pre-calculus, when you first learned pre-calculus and maybe even algebra 2, when you were looking at the exponential function, you probably thought, that's kind of a weird function. Who cares about the why is exponent? What's the big deal about exponential? Are you getting kind of a sense about why the exponential function is so important? In terms of calculus, it's actually one of the absolute most wonderful functions to deal with, because the derivative is itself everywhere. So anyways, there you go. All right, so in general, f of x is the sum of its Taylor series. In general, f of x is the sum of the Taylor series. Here's how you could write that. If we let the remainder equal the function minus the Taylor polynomial, maybe I should write that in. Remainder. That's what this is. This is the actual function. And then this is the Taylor polynomial. Remember, polynomial means it had a finite number of terms. That's true, right? You've got this function that, let's say it goes from negative infinity to infinity, like e to the x. If I cut the Taylor series off and just do a Taylor polynomial, it's going to be wrong a little bit, isn't it? It's got a little bit of slop. So this can then be translated to this. The function is equal to the Taylor polynomial plus its remainder, which again, we've hit this idea several times before. R of n, and I'm sorry, the door is standing right in the way. It's called the remainder of the Taylor series. If we can somehow show that as the limit as n goes to infinity of the remainder function is 0, it would follow that the limit of the Taylor polynomial as n goes to infinity would be equal to the limit of the function minus the remainder, which is all the way down here. It's going to give us the function itself. What we're trying to do now is kind of prove to you that this Taylor series is indeed the exact same thing as the function itself. So I'm going to throw a couple of theorems at you, and guys, I'm going to tell you right now, the next couple of theorems I'm throwing at you are minutia. That's a fancy way of saying not super important. I mean, it is, but it isn't. These are kind of the little details. Theorem 8 says, if the limit of the remainder function as n goes to infinity is equal to 0, well, that's kind of like that limit definition. Remember we talked about the limit definition of a derivative and the limit definition of an integral? This is kind of like that same thing. So we've kind of got this, the distance from x minus a has to be less than the remainder. Look at theorem 9, the Taylor inequality. This one we will use, okay? Here's what this one is saying. We know that the remainder of the function, the Taylor polynomial remainder, I guess, this remainder function has to be less than some value m divided by n plus 1 factorial times the absolute value of x minus a to the n plus 1. Can you hold this right here kind of in your head for just a second? Hold this right-hand side of this inequality in your head for a second. I gotta go back one more. I don't want to hand you right. I gotta go back one more. Sorry. Remember this guy?
Yeah.
On the bottom, it was just n factorial.
Yeah.
Here was just x to the n. And then up here, it was the nth derivative at 0 in that case. Go back to where we were. There we go. Instead of the n plus, or just the n factorial on the bottom, it was the next term after the nth term. Here it's just the next term after the nth term. It's that same idea we've already seen that we talked about Taylor polynomials.
Wait, so it's,
Yes.
it's just saying that the remainder has to be less than the next term?
Correct. It's exactly what it's saying.
The next term of the
Taylor
function,
series,
the
of
Taylor
Taylor
polynomial.
series.
The Taylor series, yeah.
So the Taylor series has infinitely many terms.
Yeah.
But if we stop at any point in the series, there's going to be a little bit of slop, a little bit of remainder. So wherever we cut it, we've now made a Taylor polynomial. And it is guaranteed, according to Taylor, who is a mathematician, that the remainder has to be less than this quantity. Now, he has not really told us a whole lot about an m, but he told us right here. Remember, that's that formula for the coefficients. Remember the coefficients formula? Yeah. Now notice instead of the nth derivative, it's the n plus 1 derivative. So it kind of makes sense. Very scary looking, right? In fact, if you're like already getting overwhelmed with this, I would just recommend just kind of hold your breath for a few minutes. And then here's theorem 10. Here's the big idea. I should say this is the big idea. This is the key to being able to prove what I'm getting ready to prove here on the next slide. We want to be able to prove that the polynomial is indeed equal to its Taylor series. This is a fact. For any x, once you pick x, for any x, if you take the limit from n to infinity of x to the n over n factorial, it is equal to 0 for any real number x. And just to let you know, factorials grow faster than exponentials, which is kind of hard to understand, but it's true. So we're going to use that on this next example. So now what I'm going to try to do, hopefully I do a good job. I'm going to try to prove to you that f of x equals e to the x is indeed equal to the sum of the Taylor series. So now what I'm going to try to do is prove that that Taylor series we got is indeed exactly the same as the function. Okay, so I'm going to say that the remainder at the nth term, absolute value, is less than or equal to, and I'm going to erase this e to the, actually let me write n here. I'm going to erase this here in just a second, okay? So you maybe don't want to write this in. I'm going to put n here for now, okay? And that kind of looks like an e. All right, that's just n. Just I'm sticking with the formula here. And then absolute value of x. And remember, our center was at 0. Remember when we did this one, we did a Maclaurin. That's the Maclaurin. So the center is at 0. And this is from theorem 9, I believe, is what I think it was. Theorem 9. There's that remainder definition. Okay. Now I'm going to make a note, and here's where I'm getting ready to change this. Let me do it in purple. So I'm going to put note that in this example, I'm going to let n equal e to the theta, where theta is just some number. Right? Like on the first one I did, m was, or theta was 1. So it's just e, or actually it was 0, wasn't it? It was 0. So it's e to the 0, which is just 1. When I had you guys do example 2, it was 2. So that constant was e to the second. Okay, so now I'm going to erase what I just did up there. I'm going to leave it in purple though. So in general, it's going to be e to the theta, where theta is just some number, natural number. Okay. Okay, so this is kind of like, I'll call this step 1, right? So now, step 2. I'm going to say that the limit as n goes to infinity of e to the theta over n plus 1 factorial, absolute value of x to the n plus 1, would be equal to e to the theta limit as n goes to infinity of 1, oops, not 1. I'll just leave that as absolute value because that's what I'm trying to get here. I'm just going to rewrite this second term here. So this is going to be absolute value of n plus 1 over n plus 1 factorial. So the only thing I did is I pulled that e to the theta piece out, because it doesn't have anything to do with n. It's a constant, depending on whatever value of n or theta you picked. Now, important observation. What does this limit have to be? I have a constant times the limit as n goes to infinity of the absolute value of n to, or x to the n plus 1 over n plus 1 factorial. What does it have to be? Has to be 0. So this goes back to this piece right here. I said this is the key that's going to get us where we want. This has to be 0 by theorem 10 on these slides, right?
Factorial is going faster.
Correct. This denominator, no matter what x you put up there, is going to grow faster. That's exactly the right way to think about it. And now we're almost done. Not quite the same color green. Here we go. By the squeeze there, guys. What's this right here? What did we just show this to be? We just showed this to be 0. You know what I think I just did? No, I'm good. I'm good. We just showed that this is 0, right?
Yeah.
What does that imply about the remainder?
There's
That it's
0.
0.
What? Can you remind me of what the squeeze theorem is?
Yeah, just 1 second. Therefore. I can remember what I wrote. I think it was x to the n over n factorial. Good. Okay, the question is, what's the squeeze theorem? I'm not going to screw up my notes here. In fact, let me come back to the squeeze theorem thing, okay? So I started off with theorem 9, which was the definition for remainder. We know that the remainder has to be bounded by the next term in the Taylor polynomial. The remainder has to be less than or equal to this. Then in step 2, we showed that this was equal to 0 based on this fact. If this is 0, if this limit is 0, what is the limit of this? Well, if that's going to 0, this has to go to 0 because the squeeze theorem compresses everything that's between it. By the way, notice that this had absolute value symbols, right? So it has to be positive. Is there anything less than 0 that's positive?
Less than e.
Right. So the squeeze theorem, just to kind of, maybe I'll go on to this next slide. I think I maybe gave myself an extra slide here. Did I do that? Yeah. Oh, okay. Is there anything else on this one? Okay, cool. So here's what the squeeze theorem is. So let's say you've got some crazy function that does something like this. I'll call it f. And you're trying to figure out, what's the limit of f as n goes to infinity. You don't know what it is. But you know that you have some curve here that maybe does this. And let's say it does that. We'll call this one h. And we know that the limit as h of h as n goes to infinity is, let's say, 1. And we know that h is greater than or equal to f for all numbers, let's say. Okay, great. Now let's get purple. And we'll come in like this. And we'll call that one L. I'm going to call it L. Oops. All right. There's L. Can you guess what I'm going to say about L? The limit as h goes to infinity, or not h, as n goes to infinity of L. I'm going to let that limit be 1. And furthermore, I want to tell you that L is less than or equal to f for all numbers. Now, by the way, let's just pretend again that f is some crazy, bizarre function we know very little about. But we know the h function is always greater than or equal to it, and the L function is always less than or equal to it. And I know that the limit of the h function is 1. And the limit of the L function is 1. Guess what the limit of the f function has to be? It has to be 1. It's squeezing, the upper and lower functions are squeezing that limit of this middle function. What were you gonna
If
say?
L was 0, would it just have a possibility from B?
Yeah, so then you don't really know.
You can't use it.
You can't, because, and you might want to say, well, I just know that it has a limit. Well, you don't, because remember, if something alternates, then, you know, maybe somehow it alternates between 0.2 and 0.8, 0.2, 0.8, 0.2, 0.8. That's not a limit anyways. So the key is that this guy here and this guy here have to have the same limit. But that's how the squeeze theorem works. So if we go back to our example here, I know that this has to be some finite amount that's positive. I'm showing that this goes to 0. If this goes to 0, it forces that to go to 0 by the squeeze theorem. Was it last year they had a couple of questions on the squeeze theorem on the exam? Maybe 2 years ago. Okay. Yeah, squeeze theorem, they kind of skipped it for a couple of years, and then 2 years ago, I think, they do it on the exam, and it got a lot of people. Because it's kind of a minutia theorem. Okay, I got a couple more things here to talk about here. Let's see if I can speed this up. Oh, okay, so let me get back to the point of this. Let me go back to this last slide one more time, just to make sure everyone's clear. The point of this example was me trying to convince you that this is indeed equal to that exactly. Not close, not kinda, exactly. And by the way, let me circle the important piece here. This is not a Taylor polynomial, this is a Taylor series. And then you might argue, well, Mr. Allen, can we ever really go to infinity? You're right, we can't, but theoretically, we'll pretend we can. Okay, moving on. Oh, by the way, let's say you want to know what is E. And when I say E, I'm talking about the constant E. If you wanted to figure that out, well, we just found that e to the x was equal to the sum, n goes from 0 to infinity, of x to the n over n factorial, correct? So what if I wanted to find e to the 1? Guess what I'd put in for x? 1. So then e to the 1 would just be the sum from n equals 0 to infinity of x is now 1. So that's just 1 on the top. That's what we have right here. And that's how you could find the value of e. Now, technically, this is irrational. Technically, it's transcendental. In other words, it cannot be written as a fraction, and it also cannot, it's not the solution for any algebraic equation. And by the way, how many terms would you have to literally write to get the exact value for e? Infinitely many. So obviously, at some point, you would have to cut it off. My guess is they probably know billions of terms of e. No one knows all of the terms of well. No one knows all of the terms. But this is how we could approximate it. By the way, e ranks right up there with this one. Anyone think of any other special numbers in math? I'll give you another one that's an important one. This one here, that goes back 2,000 years ago, and actually, there are some people that say that doesn't exist. By the way, if you don't think that exists, then you don't think that that exists, and you don't think that that exists either. By the way, pretty much most of the math that we do today, if you don't believe in these things, we have a problem. Yeah. Anyways, this is a superstar. Right up there with pi, square root of 2. Do you want to think of any other numbers? You guys ever heard of phi? Constant phi has to do with the Fibonacci sequence. That's another big one that comes up a lot. Anyways, I'll save that for another day. Okay, find the Maclaurin. Okay, guys, I'm going to have to like really go quickly here. Oh, good. I'm going to cheat. I remember I got this one I kind of filled out. You ready? Most of this slide is already filled out. Thank goodness, because we need the time. Our function here, and I'm just going to tell you right now. Here's that second bullet point. I'm going to try to show you where the formula comes for the binomial expansion series, binomial series. So what I'm doing is, by the way, guess what x plus 1 is called? It's called a binomial because it has two terms. This is a binomial. And guess what I'm doing to that binomial? I'm raising it to some power k. I want to find the Maclaurin series for that particular polynomial. Okay, so, and I'm going to kind of skip through this. We could pretend that we're doing this, and by the way, let me just do this first. Here's the first one, right? Here's if we don't do anything, right? If we just leave f alone and you plug in 0, you get 0 plus 1, which is 1. Does that make sense? Now, let's do the first derivative. To do the first derivative, where does k have to go? Goes to the front. What do we do to the k? Minus 1, right? Power rule. So when I do f prime of 0, if you put 0 in there, you get 1. So that's just going to be k, because 1 to any power is just 1, right? And 1 times k is just k. What if I did the second derivative? Well, you'll still have this k, but now you're going to have this extra factor. There's that whole factorial thing coming out. And now it's going to be k minus 2. And so then we get this, and then we get this. On the nth term, we're going to, now here's where I want you to note that last piece. Notice that on the second derivative, we didn't stop at k minus 2. We did the one before minus 2, which was minus 1. Does that make sense? So if I wanted to find the second one, I would stop at, well, if I put 2 in there, that'd be 2 plus, or it'd be negative 2 plus 1, which is negative 1. Does that make sense? This is not intuitive. I want to point that out. Okay. Okay, now I do need to fill in this slide. Okay, so let's do red. F of x equals 1 plus x to the k. This is going to be equal to the sum from n equals 0 to infinity. We're going to do the nth derivative at 0 over n factorial of x to the n. That is our center. Remember, we're doing Maclaurin here, right? Center is 0. That is going to be equal to sum from n equals 0 to infinity. And here's where the fun part goes. Guys, if you don't mind, I'm just going to go ahead and write this part right there. And I'm going to write the denominator. That's going to be super easy. That's just going to be n factorial. But guess where this guy is going to come from? All of that junk I had on the previous slide. So it's going to be k minus 1, k minus 2. I'll write one more. K minus 3. And then I'm going to put dot, dot, dot. So we're going to continue that product. And then k minus n plus 1, that last term. This is the nth derivative. We just showed that on the previous slide. That purple stuff, that's the nth derivative. Those are the coefficients. Now, let's talk about the ratio test. Let's do the ratio test. Okay, so that's going to be the limit as n goes to infinity of a sub n plus 1 over a sub n, right? This is going to be the limit as n goes to infinity. Now, we're dealing with a sub n. That's this stuff in green, right? That's a sub n. Okay. K minus 1, K minus 2, dot, dot, dot. K minus n plus 1. Now, I'm going to write this in a different color to make it stand out. This last term here is going to just be K minus n. The bottom is just going to be n plus 1 factorial. Actually, I'm going to write, if you guys don't mind, just to save, so I don't have to write this again and you don't have to write this again. The bottom, instead of writing it as n plus 1 factorial, you know we're going to try to get stuff to cancel, right? So I'm just going to go ahead and write that as n plus 1 times n factorial and save myself from having to rewrite that again. Oh, and then I got to remember this red thing, right? And can you guess how I'm going to write x to the n? X to the n times x or something like that. So I'm going to go ahead and write that up here. I'm going to write x to the n times x maybe. Maybe I should extend that a little bit. And now I'm going to do what? Multiply by the reciprocal of the original thing here. So this is going to be n factorial and then x to the n up here. The bottom is going to be all of this purple stuff again. I'm not going to write all of it. I'll write some of it. K minus 1, dot, dot, dot. And then we're going to stop at k minus n plus 1. Good morning.
Wouldn't x to the n be out of line?
It would be. Thank you. It would be. Mason has made an important note. If it's x to the n plus 1 on the top, then the x, okay, so let's write that in red down here. I'm going to kind of, maybe I'll put it in the front, yeah. Sorry. Thanks, Mason. You just saved me from making a mistake. Let me erase that top part. Just scoot it over. That's green. And I think this will be back. Okay. Now, what's going to cancel? Almost everything, right? All of this green stuff's going to cancel. All these K's are going to cancel all these K's except for the purple one, right? That x to the n will cancel this x to the n. The only thing we'll be left with is x in the numerator. The n factorial here is going to cancel the n factorial down there. So now we can quickly jump to the following. The limit as n goes to infinity of, I'm going to go ahead and write the absolute value. I think we had an absolute value of x. And then we're going to have, I think, k minus n over n plus 1. If I'm not mistaken. And I really don't need absolute value symbol there, but I'll leave it there. Good. Now, how are we going to deal with that k minus n over n plus 1? What's the trick? How do we get those, how do we find that limit?
Just do that.
Well, if you plug in infinity directly, it doesn't really help you. What's the trick? You guys remember this?
Divide by n.
Correct. You're going to divide by n. So this is going to be the limit as n goes to infinity. In fact, if you guys don't mind, I'm going to go ahead and pull that absolute value thing out here to the front of x because it really doesn't have anything to do with n. I'm going to put that in the front. That absolute value of x doesn't have anything to do with n. And you might say, well, Mr. Allen, k doesn't either, but k is not a variable, it is a constant. So now we're going to have k over n minus 1 over 1 plus 1 over n. And I really don't need absolute value symbols there, but I'll just leave them on there just for that. Now, as n goes to infinity, what are you going to get? It's going to be 1. What's the only thing that's going to be left? Absolute value of x. That's the absolute value of x. So this is going to tell us that our radius is 1, and our interval of convergence is going to be negative 1, 1. This is the Maclaurin series for binomial expansion centered at 0. Here is our radius of convergence and our interval of convergence. Now, you might be looking at this right here and feeling pretty intimidated by all those K things. I'm going to show you something. Mason, have you guys done combinations? Okay, cool. So this is, if you've had finite or stat, anybody in stats? Have they done it in stats yet?
Yeah, but we don't go over it again.
So these are called combinations. And it should look very familiar. So we would say, like, and your calculator actually will do this. Like, you could do 7 combinations 2 at a time. And that's equivalent to, say, 7 over 2. Some books write it this way. I've always pretty much used it this way. But a lot of the higher level math classes will write it this way. These are called binomial coefficients. In other words, on our next slide, here is our binomial series. I've already shown you why the radius of convergence is 1. So the interval, the radius of convergence is 1. If we're centered at 0, then it's going to go from negative 1 to 1, not including those endpoints. Here is the general formula. And here it is expanded. I think this might be the absolute hardest thing for students to remember because they're just not familiar with this guy. I maybe should give you one more formula for combinations. It's n factorial over k factorial and then n minus k factorial. Is that right, Mason? Is that, you remember that right formula?
Looks right.
Yeah, I think it is. So for example, earlier when I said 7 things 2 at a time, you got your calculator handy. Mason, when you do 7 combinations 2 at a time, let's see if this is right. Okay, let's see if we got that right. Good. Just to let you know, there's a formula there. I'm just telling you right now, if you are going to go anything in college related to math, you're gonna have to know this these binomial coefficients for this combination. You're going to use it whether you're in engineering or math or whatever. So it will come up. Okay. All right, guys. I'm going to skip to the very last bullet point, and I'm sorry I went over now. We're over time. I just want to talk about these last 2 examples. And they'll go quick. I'm not going to go into all the detail. Most of it's already done for you. So we've already seen this one here, right? There's that geometric series thing that we used when we did power series. That's that A over 1 minus R thing. In this case, A is 1. We've already seen that. Today, we've seen where the exponential function falls into play using our techniques from today. And actually, you can go back to section 8.7. Hopefully you are familiar with these 2 guys here, the sine function. Notice that the sine function, which by the way is an odd function. You guys remember what an odd function is versus an even function? An odd function is symmetric with respect to the origin, if you will. So, and then an even function, like cosine is an even function, it is symmetric with the y-axis. And by the way, here's another kind of clue why cosine is an even function. Look at all the powers in here. Forget the 1, but what is everything in the cosine function? It's an even exponent. Look at the sine function. Everything is what? Odd. So that's kind of an indication why the sine function is an odd function and the cosine function is an even function. Anyways, here's some more. Okay. Now I'm going to come back. I'm going to use these top 3 or 4 here to do an example. So I'm going to find, so let's say that f of x equals e to the x sine x. Okay, well, what was e to the x? We just did it. What was e to the x? It's right here, right? It's 1 plus, right? 1 plus x plus x squared over 2 factorial plus x to the third over 3 factorial, sorry guys, plus x to the 4 over 4. Anyways, you guys get the idea, correct?
Yeah.
That came from this list of well-known Taylor series. What about, I think the next one I said was sine, right? What about sine? Well, we just talked about sine. Sine was all the even powers, right? I'm sorry, not even powers, odd powers, because it's an odd function. So then for sine, I'll do that in a different color. So sine, we're going to have x. And then, oh, by the way, I should also mention, notice that it alternates. They both sine and cosine alternate, which kind of makes sense, right? The sine function goes up, and then down, and then up, and then down. So then x to the third over, and then 3 factorial, right? Just reading right off of my list, and then it's going to alternate to plus x to the 5th over 5 factorial, and then minus x to the 7th over 7 factorial. Oops, I forgot my dot, dot, dots. Don't forget your dot, dot, dots. Dot, dot, dot. Now, you're looking at that thinking, okay, Mr. Allen, what the heck am I supposed to do with that? We'll go to the next slide. So, hopefully you kind of remember how to multiply this way. Do you guys remember how to multiply?
No, I never learned that.
Okay, I know some of you do lattice method and all this stuff, but anyways, here's the idea. What's x times 1? What's x times x? What's x times 1/2 x squared? Well, it's 1/2 x to the third, right? What's x times 1/6 x to the third? Then the next piece is we have to do those, all of those, infinitely many of them, which I know would be impossible. But now, what about this one? What is negative 1/6 x to the third times 1? Well, it's negative 1/6 x to the third. What is negative 1/6 x to the third times x? Well, that'd be negative 1/6 x to the fourth. And then what you do is you just add those up. So this, in fact, I'll write the general formula here for you. Here's the answer. So f of x equals e to the x sine x is equivalent to, and now I'm just going to read these terms. It's going to be x plus x squared plus 1/3 x to the third. Let me give you another term here. Oops, the next term is minus. The next term is minus 1/30 x to the 5th. I'll give you one more. And it goes on. And the next term actually turns out to be minus as well. So that would be the Taylor series for the function e to the x sine x. So what we did here is we have a product, if you will, of two functions. By the way, this one is transcendental. This one is trigonometric. And we get a nice infinite series just going term by term. Okay. Is this something that you should memorize? Absolutely not. Okay, so last one here. Okay, so let's go back and make sure I remember what our first problem. Oh yeah, tangent x. Okay, so now we got to do tangent x. Last thing here. So now I want to do the tangent of x. Okay, well the tangent of x. Well, what's tangent the same thing as? Well, isn't it sine x over cosine x? I mean, that's what it is. That's what the ratio is. Well, what was tangent x again? Or what was sine x again? X minus x to the what? Cube over 3 factorial plus x to the 5th over 5 factorial minus da da da, right? That's what sine x is. What about cosine x? 1 minus x to the 2nd over 2 factorial, because it was even, remember, it was even. Then what? Plus x to the 4th over 4 factorial, then minus x to the 6 over 6. Anyways, you get the idea. Does that make sense? So the previous example, when I had e to the x times sine x, I had to do a product. So guess what I'm going to have to do here? Right. Polynomial long division. So now here's what we got to do. Remember, when you divide this top thing, this is what goes inside the division box, right? This bottom thing is the divisor. It goes on the outside, so that's what we've got here. So this on the inside here, that was the sine function. This out here, this is the cosine function. Now let me just explain a little bit on this problem, how you would get your answer. So the first thing you do is you look at this x and this 1 and you say, what times 1 would give me x? Well, the answer is x. X times 1 gives me x. So I would have to take x times this entire polynomial. X times 1, well, that's x. X times 1/2 x squared, well, that'd be negative 1/2 x to the 3rd, right? And then I'd have to take another power of that, so that'd be x to the, does that make sense? Great. Then guess what you have to do? You have to subtract. You take this, subtract this, and guess what x minus x is? 0. Then you got to take this minus this, which gives you this, and this minus this, which gives you this. Now you have to play the game again. In fact, let me erase what I've done here so far. Now we're focused on the next piece, which would be this guy. What times 1 would give you negative 1/6 x to the 3rd? Oh, I'm sorry. That's wrong. I said that wrong. I said that incorrectly. Sorry. It's the new equation. I said that incorrectly. This guy. What times 1 will give you 1/3 x to the 3rd? 1/3 x to the 3rd. So it's actually pretty easy. And so then you just go on down the line here. So then you're going to take this times this. So you'd have to take 1/2 times negative, 1/3 times negative 1/2, which would be negative. Then that's going to be negative 1/6. You see where the negative 1/6 comes from. And then, of course, you got x to the 2nd times x to the 3rd. That's x to the 5th. And then you would keep going down the line. This up here, this is the answer. In fact, I think I've got a couple more terms for you. So I'm telling you that the function tangent x is equal to x plus 1/3 x to the 3rd plus 2/15 x to the 5th. Anybody want to take a stab? Is a tangent an even or an odd function? Well, look at the exponents. It's an odd function. I'll give you the next term here too. The next term turns out to be 17 over 315 x to the 4th, or to the 7th, sorry. Can't be 4th, right? Because 7 is odd. 7. And I can give you the next term too. Don't forget your dots. Oh, by the way, you might say, Mr. I already knew that. I'll come back. Remember that table I gave you a few minutes ago? That was, well, I guess I didn't give you tan. That's tan inverse, my bad. There's tan. Cool. Guess what?
How often am I going to use that?
Done. Chapter 8 is done. Oh my God. Woo. That's all I got for you guys. Thank you for your patience. I know that was a lot. Really not a lot of new concepts. I spent probably more time than necessary talking about some of the proofs. But that's it. We are done with chapter 8. I'm going to mute myself and let my voice take a break, and then I'll take questions if you have questions.